The next speaker is Mathis Bouverot-Dupuis, who will be telling us about Sulfur, which is a re-implementation of something like Autosubst.
Okay, is the mic working? Okay, so hello everyone. So I'm actually a first-year PhD student in Paris, working with Yannick and François. But today I'll be presenting work I did with Théo, Kathrin, and Kenji before my PhD started on Sulfur, which is a Rocq library. Okay, so we know since the PoplMark challenge that a super annoying aspect of formalizing the theory of programming languages and type theories are binders. So when you work on paper, you think of variables and binders as names, and you work up to alpha-equivalence. But it turns out alpha-equivalence doesn't work super well in Proof Assistant. And you can see if you just, I was curious, and you look at the kind of proposed solutions to the PoplMark challenge, there's almost as much binder representations as proposed solutions. Yeah, so there has been a lot of work on this. And one such particular piece of work that this talk is based upon is Autosubst. So Autosubst is also a Rocq library developed by many people, including Scheffer, Tebby, Smoker, Kathrin Stark, which is a co-author, etc. It has many implementations, and actually many people don't know this, but if you want to use one, it's probably the OCaml version, which is the most feature complete. And it has been used successfully in many formalizations. So quickly, I'll give like a crash course on Autosubst. So let's say you want to formalize the meta theory of system F. First step is to write the grammar of types and terms in a format that Autosubst understands. You give this to Autosubst, and Autosubst, well, first generates inductive types representing your grammars of types and terms using the Bruijn indices. Then Autosubst will generate a substitution function. For instance, this would be the parallel substitution function, which substitutes all the Bruijn indices at the same time. Autosubst proves basic lemmas about substitution. And finally, and this will be the focus of this talk, Autosubst provides a tactic called asimpl, which is super useful. And you call asimpl, and it basically simplifies your goal using the lemmas it proves about substitution. For instance, you can prove this technical lemma, which comes up when doing, I don't remember, probably the proof of Church-Ross or something like this. And asimpl simplifies both sides to the same thing. You do reflexivity, and you're done. So asimpl is really very useful. The issue, though, is that asimpl is also super slow. For instance, on Théo Winterhalter, which is a co-author, so on his development of the type theory of ghost reflection, asimpl takes more than 3/4 of the total type checking time, which is huge. And this is because the implementation of asimpl is very naive. That's how it works. It's just a big loop where you do set-to-read rewrite with a bunch of lemmas. And set-to-read rewrite is slow. Putting it in a loop is even slower. Okay, and so the focus of this talk is to present Sulfur, a Rocq library, which is essentially a re-implementation of Autosubst using different principles so that the asimpl tactic can be more efficient. So the interface provided by Sulfur and Autosubst are very similar, so I focus on what makes it different, and that's how we implement asimpl. Okay. And the key idea to make it faster is not something super new, but it hasn't been done yet, is to use reflection. Okay, so I'll start with a simple example to explain how reflection works. Let's say you want to solve this equation. So here the square bracket syntax means apply a substitution. SID is the identity substitution. So the way you would do this is, let's say you want to use asimpl to simplify the right-hand side. This is how it would work. So the first step would be to actually change from this concrete syntax where substitution is a function and identity is a function. You verify it to something where you replace functions with constructors. So it's a different syntax where you've made many things more explicit. For instance, tsubst represents the application of a substitution to a term. SID with a capital is the identity substitution. Then you can write in Rocq a simplification function, which translates, which will go from this explicit syntax to itself and does the actual simplification. And then you can translate back using an evaluation function back to the concrete syntax. So that's a high-level point of view, and now I'll go into a bit more details on how these two syntaxes are formed. So the concrete syntax looks like this. So let's say you're formalizing the simply typed lambda calculus. You would have like a constructor for variables, which contains a Bruijn index. You would have applications and lambda abstractions. You can define substitutions as functions from indices to terms, so a parallel substitution. And then Sulfur will generate, well, Sulfur generates all of this. So you get a substitution function operations, like you can compose substitutions and so on. And then on the other side, you have explicit syntax, which makes a lot more things, well, explicit, it's in the name. So this looks a bit like sigma calculus with a bit of extensions. So you would have, so in the term constructor, you would have the same thing as the left. So you would have variables, t-var constructor. You would have this t constructor, which kind of subsumes both the app and lambda from the left-hand side. And then you have a bunch more things. You have tsubst, for instance, which represents the explicit application of a substitution to a term. And now substitutions are also verified. So you have a bunch of different cases. You have the identity substitution. You have the explicit composition of substitutions, and so on. So here there's a bunch of things that so here the kind of the tmvar and smvar constructors are a bit special because they represent kind of concrete syntax which we don't know how to verify in the explicit syntax. So we just box them using this concept of meta variable and don't touch them. And also something I won't touch in this talk, but which is present in the implementation, is that we also need to do the same treatment for renamings and for natural numbers. So we need to verify quite a lot of things. Okay. So going into a bit more details, why the concrete syntax is different for each language. So let's say you're formalizing, I don't know, simply type lambda calculus or a dependent type theory or whatever. Sulfur regenerates the concrete syntax and operations all the time. But the explicit syntax, on the other hand, is defined once and for all, and it's parametrized over a signature. The signature contains the details of the specific language. So it works something like this. So in particular, the T constructor case kind of encapsulates all of the constructors of the base language. So this would be, for instance, application, lambda, etc. And the signature contains a bit of details about the concrete language. It contains the set of constructors, for instance, app and lambda. And for each constructor, the number of arguments and which arguments contain a binder. So essentially, the signature contains the binding structure of the language. Okay. Then just a bit more details on asimpl. So the input is a term t in the concrete syntax, and you want to produce a term t prime in the concrete syntax and a proof that both are equal. And the way it works is that you write the verification function from concrete to explicit, and this has to be done using metaprogramming. So in the implementation, I use the Camel plugin. Then you have the other way around evaluation, which goes from explicit to concrete syntax. This is a Rocq function. And it takes as input an environment, which is related to meta variables. It contains an assignment from meta variables to concrete terms. And then the nice thing is that since the explicit syntax is simply Rocq inductive, you can write the simplification function as a Rocq function, and you can prove a soundness theorem for this function. So if you have a term t in explicit syntax, evaluating t or evaluating the simplified version of t gives the same thing. And it's because we can prove this procedure correct once and for all that you get efficiency benefits, because you don't need to build and type check a large proof every time you call asimpl. Okay. Another benefit is that since the simplification function is implemented in Rocq, it should be quite easy to extend. For instance, the current version is quite naive, but it shouldn't be too difficult to make something a bit more efficient. The kind of the hard parts are the metaprogramming parts, so like the verification function. Okay, so that's kind of how it works. But then future work, so Sulfur is still slightly work in progress. In particular, something we haven't done and we really should do is doing benchmarks. So the performance is noticeably faster than asimpl. We just don't know how much. I would guess probably at least 10 times, but we really need to do benchmarks to know. And we still have a couple of basic optimizations to implement. I said the simplification we use is very basic, but we also had some issues with rewrite strat, which maybe we can talk to with the developers afterwards. Okay. Another difficulty, and this one is a bit more fundamental, is that scaling this reification approach to more complex languages is sometimes unclear how to do. For instance, handling multiple sorts in a system F way is not something we support for the moment. So for the moment, Sulfur is more suited to formalizing dependently typed calculi and stuff like this. But it's not clear to do it's not clear what to do in this case. And if you're interested, we can talk afterwards. Another feature we'd like to support is having an array applications and in general arbitrary functors in the term syntax. Okay, and then the last direction for future work, more on the theoretical side, is that we would like to have a completeness theorem. Because in fact, in simpler variants of sigma calculus, there is a completeness theorem in this paper by Scheffer, Smoker, and Tebbe, which essentially says that if you have two terms in explicit syntax and the evaluations are the same, then you can join them via simplification. And intuitively, this says that asimpl should be enough to decide equality of concrete terms. Unfortunately, this does not hold in our case, and there's some interesting future work here. Okay, so just as a recap, presented Sulfur, which is essentially Autosubst with efficient simplification, but handling multiple sorts is challenging. Thanks.
Hi, thanks for the talk. Asimpl also does a thing, and I'm not sure whether your tool does this, so this is the question. Asimpl also does the thing where it looks at the goal and finds all the occurrences of terms and simplifies them all. Do you also walk the entire term to find all the things to simplify? And if yes, how did you implement that?
So in a way, yes, but that's where we had limitations with, so at the moment we use Rocq's rewrite strat mechanism. And this poses some issues because you want to avoid simplifying too much, because if you simplify a term, you don't want to simplify directly its subterms. Otherwise, you're just going to walk terms several times. So it's not clear to me what we want to do here. If you have ideas, I'm interested.
When you say from an efficiency point of view, is the thing that's slow the actual rewriting, or is the thing that's slow checking the proof term, or is it both?
I don't know yet. We really need to do benchmarks. Yeah.
So, did you guys also look at just an implementation of the repeat first rewrite strat thing? Can you just replace the whole thing with a single call to rewrite strat? Which does term traversal and rewrites everywhere, right?
Compare this directly to rewrite strat?
Yeah, an implementation.
Yeah, that's what we need to do, yeah.
Okay.
Yeah. I still, just a question of time.
So, how hard would it be to hook onto your evaluator to add, for instance, beta equations? Probably you would have to add some few or some sort of easy termination argument, but then you would get an evaluator not just for the substitution calculus, but for beta sigma. Yeah,
so that's what I mean when it's very easy to extend. I think it would be actually really easy to do this. So yeah, the only slight difficulty is with respect to termination. For the moment, I've kind of built the simplification function in a way that it's obviously terminating. It's structurally recursive. Not sure that's the way you want to go. Probably you want to use fuel, and then you just don't care about termination. Yeah.
Are you forced to write your syntax in Autosubst style, or can you retrofit it on existing formalizations?
You can use anything. We just chose this for simplicity. We could also choose the format of Autosubst 1, which is a bit different, more like inline style. Maybe you want to support different things. I don't know.
Okay.
Yeah.
It also reminded me a lot of squiggle EQ. Do you remember? Do you know about this thing that was developed, a kind of generic syntax like this to develop House by-simulation relation. I don't remember what it's called right now, but it uses a similar syntax, and there might have been simplification tactic also at the time.
Okay, I'm not
it
too
was from
familiar with
Abhishek
this.
Anand and Vincent Rallier, I think. Yeah, you can look it up.
Okay, we have time for one last question, if there is one. Okay, so let's thank Mathis.